Okay, if you can see all that, I think we'll get started. So first off, are there any questions or any discussions that people want to have on final projects, course content, etc.? I've been fielding some emails about changing topics, which is totally fine. Tweaking the topics that you have, that's fine too. Making sure that you hone in on something you're interested in that still relates to the class. I mean, we would have a hard time justifying a final paper and presentation on powder bed fusion of metals in this class. But I think we've talked enough about different types of additive processes, about different types of polymer and composite materials and their uses. We'll talk about applications some more. And so my message is that I'm flexible on topic as long as it relates in some way to the class. And also picking a topic is part of the assignment. And so, I'm willing to brainstorm it with you and throw out ideas, but really doing that digging, thinking about what your interests are, thinking deeply about the class material. I mean, don't discount the work that has to be done in order to get a topic that you're interested in. So, it's not like I just assign you a topic and the world is good. You really want to use this opportunity to help advance your thinking process on how to pick a good topic, on how to identify things you're interested in, how to find literature to help support the direction you want. Because sometimes in the real world, your boss will come and say to you, we need to find something to work on that improves the company. Why don't you go figure that out? And that's a very hard assignment. Hopefully that's not your very first assignment, because you have to, uh, you know, get familiar with what the company or organization is. But as you progress in your career, you will take on more and more roles that are open ended. How to make our products better, how to improve efficiency at the company, what new directions should the company take in order to launch new projects to make money. How do we grow the business, so to speak? And so I think that while this isn't a completely open-ended project like that, sort of these assignments that take some work on your part to figure out how to go about the assignment really sets you up for success in the future. And of course, that's what we're trying to do here at the university, is trying to give you some tools that are useful. So not only do you have the knowledge in the class and now familiarity with these topics and are conversant in the vocabulary and some of the processes, but the thought processes and the work that you do on your own behalf is just as important as what we talk about in class. And so don't forget about that part of the assignment as well. But again, I'm happy to brainstorm. I'm happy to trade emails. And if you want to change up your project, you're free to do that at any time. But the sooner you cement something and start getting some things on paper, the sooner or the easier it will be towards the end of the semester. You're welcome to change in the last week of the semester if you want. You'll just make it harder on yourself. So any questions or comments on that? I still have a couple of feedbacks to give on your assignments, and I'll push on those. I've been busy with 3D printing masks and other things for the worsening medical situation, but I promise I will stay engaged on the homework and give you the feedback you need to be successful in the class. So any questions or comments or things people want to talk about? All right. So what we're going to do is we're going to finish up 4D printing here a little bit. We've talked about structures, auxetic structures, metamaterials, interesting lattices, interesting things that can be done with additive manufacturing. And that's applicable to additive of lots of different materials. But a lot of these cool demonstrations have been done in polymers and composites with SLA or with direct ink writing or material extrusion AM. And so I want to finish up 4D printing because this is really the future of how mechanical design and biomimicry is going to be done for things like soft robots, autonomous vehicles, advanced architecture, maybe advanced medical devices, as we saw these unfolding stents. And so I want to make sure that you're able to link up some of these concepts with advanced manufacturing techniques and materials that we've talked about in class. And so that's why we're going into the weeds a little bit here on something like this, which is this biomimetic twisting flower design right here. And so we'll finish this up today, and then we're going to move on a little bit and talk about some manufacturing issues, talk about some issues of using additive processes in different industries like aerospace and biomedical. And we're going to talk about safety issues with additive. And so for those of you that are only going to take one additive course, this will be pretty useful to define the landscape of additive. For those of you in AMD that are going to take 5 or 6 different additive manufacturing courses, there will be some basic information in here. And so I encourage you to think about what's useful in the coming lectures. And then if, especially if you already know all this stuff, or if it's covered in other classes, it's okay to give me a heads up and say, oh, Professor Joshi talked about this. And so that's useful for the AMD students and people that are going to take more than one additive class. But I want to give some basic additive manufacturing industry information to those of you that may only take one additive class in your whole academic career. And so bear with me, and if we get off track, it's fine to tell me by email or in lecture, oh, we've covered this, and so I'm happy to take that feedback. Or would you please talk more about aerospace materials, because half the class is going to get a job in the aerospace industry or something like that. I'm happy to tweak the last few weeks of the semester so it's useful to you. So anyway, we'll finish up this idea of structures, and I think we ended about here, where depending on shape memory effects in the polymer, and depending on whether you're 2 material printing or 1 material printing, or how you fold something like this bunny rabbit right here, how that can be folded in an origami sense, there's a lot of potential for using these concepts of folding and bending, and shape memory materials in order to do cool stuff that you really just can't do with conventional materials that are in general static or conventional fabrication techniques where nothing changes. And this is really what people are thinking about for the next generation design of products. And you can even start to see this in terms of phones that fold, or flexible screens, or morphing wings for aerodynamic control on advanced automobiles. You know, these active and smart materials is really where the world is trending in terms of advanced products. And this is how those concepts are developed. So this is a cool one right here, where rather than just folding up boxes and pyramids, and so you see these canonical shapes. This is a cool paper because they print this airplane, this plastic airplane. It's not a paper airplane, but they print this airplane flat, and then they cool it down, and it folds itself up into a structure that can fly. And you can imagine that this might be very interesting for autonomous sensing. This might be very interesting for, say, environmental sensing. So this is cool. And what's interesting about this specific example, if you read this, is that even something as simple as this folded airplane design has 2 opposite directions of curvature. So you have the center curvature, and they call that theta 0. So that folds up in one direction. But then the theta 90 degrees, so here, let me, right here. So this fold, or the center fold of a paper airplane, is in one direction. And then the wing fold, this theta equals 90, is in the opposite direction. So this is two different directions of folding, which is different than this single direction of folding in this rabbit example. And so there's lots of really interesting mathematics to think about what can you do with one direction of folding versus what can you do with bidirectional or two different directions of folding. And then if we go back to the example from Harvard, how do you get these complex curvature shapes? There's two different curvatures in this lily flower. How do you get that from a certain print path? And how do you get that from a flat object to begin with? So if you're interested in origami, there's a really cool Nova documentary on that. I'll try and put that in the discussion group if I remember. But this now is getting into how do you fold up complex shapes, or how do you obtain complex curvature from flat objects. And so there's a whole branch of mathematics devoted to this, and then material scientists and engineers and product designers and 3D printing engineers really make this a reality. So that's a cool demonstration and something for you to think about as we move forward. So this paper right here, I just wanted to bring this up because I think we're getting to the end of these slides, although we're going to cover magnetics in a second. So this paper really leverages the idea of this bimaterial assembly, or this, in some cases, this bimetallic strip idea, whereas if you have two materials that expand differently, you can get bending moments on the material based on that differential expansion, assuming that the interface between the two materials is robust. So this is just outlining right here some of that idea. And what's cool about this is that they use a flexible and a stiff material to do that, and they print under tension. So we saw a little bit of this in the ceramic polymer SLA example, where they were putting in wires in order to get curved shapes in pre-ceramic polymers that they could turn into curved ceramics. And so again, it's using this idea of stretching in a smart way to get an idea of whatever the radius of curvature they want is. And so that's cool. And so they've demonstrated all sorts of different parametric combinations of how do you get these assemblies to curl, and how might you build something out of this these folded or curled assemblies. And so this is not necessarily 3D printing per se. This is taking a two-dimensional object like this pink elastomer here. So that's something like PDMS or EcoFlex or something like that. And they just make it pink so you can see what's going on. It's stretched in this frame, so it's elongated, and they print on stiff supports on extended elastomer. And so when that stress is released, of course, the stiff part, the curvature is towards the pink part. And so you get assemblies that look like this. And so all of these edges are curved, and this six-sided or nominally six-sided object turns into a box that folds up. So again, this is not a high-tech 3D printing demonstration per se, but being aware of some of these mechanical tricks, or these mechanical techniques, let's call them, can be leveraged in terms of multi-material 3D printing, or if you have a 2D printing process, how do you get three-dimensional objects from that? And so they showed all sorts of interesting things. And so once you know how to do curvature, once you can generate curvature in whatever way you want, and they only put the support on one side of the elastomer, but of course, if you put the white support on the other side of the elastomer, you can get bidirectional curvature. They folded up this little table. That's very interesting, and it supports some mass. So again, this is not groundbreaking in terms of a new 3D printing process, but this is exactly what people are interested in for 3D printing furniture, or for being able to ship objects that are flat, because of course you could ship a heck of a lot of these flat airfoils in a package, and then you take them out, heat them up, and then they pop into a three-dimensional shape. So whether it's shipping, or whether it's concealment, or whether it's some other motivation, like only having a 2D process that you want to make 3D objects out of, this is something that people are thinking about. And it's worthwhile for those of you out there that are either mechanical engineers or don't know anything about mechanics and you want to be exposed to some cool stuff. This is worth checking out. Any questions on this? Okay, we'll keep going, but feel free to put something in the chat or to unmute yourself and speak up if you'd like. The other interesting thing that people are thinking about in this realm, and especially with 3D printing, is how do you softly engage with organic things? Now, this paper's funny because how do you pick up a roach without hurting it? And so this doesn't often happen now. I mean, if you have a lot of compassion for insects, you might sweep the roach into a dustpan or a garbage can and set it free outside. But most people would not approach this, so to speak, with a soft touch. However, if you think about how might you train a robot to pick up a peach, or how might you train a robot to hold a human's hand, or how might you train a piece of industrial equipment in order to move animals where they need to go for veterinary purposes, you really want to think about how you make soft touch active objects in order to interface with organic things. Because right now we build robots with steel and joints and linear actuators, and those robots have a really hard time feeling, if you will, how much force a robot is using. And there's some really awesome demonstrations on YouTube, which we won't look at, so we don't have to switch back and forth, about how do you teach a robot to pick up an apple? Or how do you teach a robot to hold an egg without crushing it? And so this is one example right here, basically using the same idea as curling, but it's able to curl this soft, flexible material in blue with some polymer grippers here that are like hairs and pick up this roach or this bug, which is really interesting. So if you want to pick up grapes, or if you want to sort fruit, or perhaps for veterinary purposes, you'd really need a soft holder on the vet bed to keep the dog steady while you do surgery or something like that. So that's really interesting. And it's really interesting to think about product design in this way, rather than aluminum and motors and everything else. How do you design these soft machines? And additive manufacturing is playing a major role here because we could do experiments so much more quickly. So something to think about. There's a really awesome one. It's not this one. Anyway, there was a really awesome demonstration of this for catching tropical fish underwater. So coral habitats are under threat. And so in order to figure out what the threats are, you need to study some of the wildlife. But how do you catch an endangered tropical fish so you can inspect it? And so you might want to use a soft trap for that, because if you try and trap the fish with a hard trap with a net in a frame, etc., you can put them under stress. So there's just some really, really smart demonstrations of this, and a lot of them are 3D printed, so you should be aware of that. Same idea. How do you softly hold on to a plastic cup, and how do you create a gripper? And so this is just a demonstration of what that looks like. And then finally, we won't watch this video, but now this is using thermal or thermally responsive shape memory alloys with resistive heating. So even though this is not a polymer per se, what they did was they constructed this nickel tie mesh and nickel titanium in the right composition as a shape memory alloy that's thermally responsive. And so when they run a current through this assembly and heat it up, they can get it to change shape reversibly based on how much current they're putting in, because the current, of course, creates the temperature through resistive or Joule heating. So this is just another demonstration of all the cool things that's possible with both additive manufacturing, unique architecture, and the right material. So I just wanted to bring this to your attention, and it's a nice YouTube video. Where this is really starting to take off is in architecture. And so folks that have studied architecture or architectural engineers that are interested in sustainable building materials and smart buildings, this YouTube video, again, that we won't watch, so my PowerPoint doesn't crash here. This assembly opens and closes in response to light. And so you can imagine that this is really useful. Rather than having a shade and a motor and a photodiode sensor that raise and lower shades in a building, takes energy, it's mechanical parts, they break, all of that stuff. What if you had a window shade that just went up and down on its own that was light responsive? And so you can get shades to close when the light comes out, which in a hot environment you might want, or you can get shades to open when the light comes out, depending on how you build the response into the architecture and the material. And part of this was 3D printed, part of it wasn't, but people are really interested in using these ideas of smart materials and smart design with additive manufacturing in order to do passive buildings, or in order to not have to use all these different components that cost money, that have to be maintained, etc. And so you can check out this video as you're doing your YouTube research this weekend. But this is where a lot of smart materials and where additive manufacturing is really making inroads is, perhaps you could have window shades that respond to humidity, or of course, window shades that respond to sun, or some pavilion in a park that closes up when it rains. So it responds to water through a swelling response or something like that. And so this is just to prompt your ideas on all the different applications that are emerging based on the really useful processing capabilities of additive manufacturing. Any questions on that? Any comments?
Dr. Hickner?
Yes, go ahead.
Yeah, so I had a quick question. So do smart materials have like a limited lifespan, which they can remember a certain shape?
Yeah, no, that's a great comment, Eddie. Oh, I see your chat too. Okay, thanks for unmuting yourself. I don't always see things in the chat. So that is the magic. And so just like finding the right alloy of aluminum to put in a car, or the right type of polymer that's going to be able to last as a car tire, or materials that have all the properties, including longevity, that you need in the real world, it really wouldn't be great to make a toothbrush out of a polymer that only lasts 2 weeks. you need to find a smart material that has enough reversibility and can resist degradation for whatever the lifetime of the component is. And so, while these concepts are easy to demonstrate, something like this, this exact thing might not be very useful. And so, how do you take this basic knowledge and translate it to something that you can sell as a product or something that you can put on a building in the real world? Or, this is just someone holding up a demonstration piece to a lamp at their desk. Does this work in sunlight? Does this work for tens of thousands of times? How can I take something that looks like this? This is just a lab experiment. And how can I turn this into a useful product? And that's really the key part of how you translate engineering and scientific observations into something that's useful. But every technology started like this. I mean, there were people saying, I wonder if it would be useful to network two computers together. What might that be? In the 1970s, no computers were connected to each other. And then they thought about connecting computers, and then we had the internet. Or someone in the 1950s observed the photodiode phenomenon or the solar cell phenomenon, and they said, wow, that's interesting. When I have this heterojunction and I shine light on it, it creates a voltage. I wonder if that's useful for anything. And so we have to remember that, or back in the day, the cave people said, oh, that lightning hit our forest and this thing called fire happened. I wonder if that fire is useful for anything. And so I think we have to remember that just because someone on YouTube has shown this function, this is not necessarily ready for prime time, but this is how advances are made. There's an idea, there's an observation, and then we continue to refine and engineer and find the right material, and then eventually we're ready to go. Now, it's hard to anticipate it was hard to anticipate in the 1970s that you connect two computers together and then you get Facebook or Amazon. And so there has to be a lot done between the initial invention and widespread use. But this is, I'm trying to clue you into some of the things that people are thinking about right now. And I'll tell you that folks are using stuff like these soft grippers. Folks are using stuff like these smart materials at large scale, and they're starting to get close to real products. And so, we can talk about really esoteric stuff that we don't know if there's a use for yet, but a lot of the things in this class you're going to be seeing in 5 or 10 years, and one or two of you might pick this up for startup companies or for the companies that you work for in the future, or the universities that you work for in the future, and say, hey, that's a really neat idea. Let's work on it and see if we can continue to engineer it into something useful. And so I think that some smart materials have a limited lifespan, but other smart materials don't. And it just depends on the application, and it depends on the requirements of the application. So things are getting there. It's not perfect, but people are starting to put these smart architectural materials on things like demonstration buildings, on things like net zero energy buildings, or even buildings that are energy positive. So there's a school of thought out there that a building that consumes no energy is not good enough. You actually need to build a building that puts extra energy back into society so you can run factories and make up for old buildings that consume energy. And so there's a lot of new ideas out there in terms of the products that we make and the things that humans do in order to give additive benefits to society, not necessarily just to minimize the impact of a building or a product or something like that. You could think about, a carbon negative building. So you build the building, and carbon dioxide is actually taken out of the atmosphere because the bricks in the building might slowly absorb CO2 or something like that. So these concepts are emerging and they're getting there, but it really depends. I think just like any material science or additive manufacturing answer, it depends on the application, depends on the material.
Thank you.
Yeah, so that was a long-winded answer, but the point of part of this class is to expose you to really crazy new things, because you never know where those new ideas are sparked. And then the other parts of the class are really practical. How does SLA work? What is a photoinitiator? What polymers tend to work in SLS? And so hopefully I'm giving you a good mix of practical information that you can use and sort of far out information that might be useful in the future. So one of the pieces of really practical information is in this paper right here. And so this is a really interesting composite. So it's a biomimetic composite. And whether you're making advanced armor, or whether you're making a fender for a car, or whether you're making a consumer product that has to have strength, this type of layered composite is exactly what people are looking for advanced materials. And so we already have this because we already have a lot of composites. We have clay composites that are in the bumpers of Toyotas. That was the first commercial instance of nanocomposites, and so you can look that up. That's very interesting. But these composite materials exist all over the place. It's just when you look at a product, you don't always know it's a composite, but it generally is if it has some strength to it. But these biomimetic composites like abalone shells or bone or other things like that have a structure that's key to getting the mechanical properties that you want. And so the challenge for additive manufacturing is, how do you get this composite layered architecture, or cholesteric just means the layers are turned in a certain order because it has cholesteric order like a liquid crystal. Cholesteric actually comes from cholesterol, which is liquid crystalline material. But anyway, it has a certain order to it. Or this type of concentric order that's observed in bone and other things to give it strength. And so the question is how to print ordered composites. And one of the ways to get that order is to do stereolithography under the presence of a magnetic field. And so we have, this is DLP SLA. That printing technology exists, and all they did in this paper was they put two magnetic coils on each side of the printer so they could orient particles in the field. So they could turn the field on, and then they could solidify the layer doing UV exposure, and then they could turn the field off, etc. Or they could shift the field to get different orientation, so they can create this layered architecture, or they can create a cholesteric architecture where the orientation is different in different layers. Or eventually, if you do things right, you can get things that perhaps have concentric order, but also have porosity in them as well. And so we know that SLA has a general orientation in terms of, yes, some layering happens if you use the right aspect ratio particles, or if I'm doing material extrusion AM, we go all the way back to the Harvard study. If I'm doing material extrusion AM with these fibrous composite materials, you see the fibers oriented in the direction of the road. And so we know that there can be some order in these different printing processes, but this paper basically demonstrated how you can design or how you can force order in SLA printed materials depending on the magnetic field. And so, of course, this is a regular SLA resin with magnetically susceptible particles in it. And so you're generally going to use, let's see, I thought they used iron oxide. Where does it say? Anyway, right here. So they'll use, well, so they use alumina is one, but I thought there was iron oxide in here. Anyway, you have to have some particles. So particles need to be magnetically susceptible. Everyone in magnetics knows that, but I thought I'd point it out. I think there's another example here that they're going to talk about iron oxide in a second. But now this is cool because you can, within a voxel or within a solidified region of material, now you have an anisotropic composite and you can design that in. So you can print stuff or you can print objects with different orientation in different places rather than having to deal with the inherent orientation of the printing process itself. So if you're interested in this idea of, if you're interested in this idea of unique printing processes where you can create order within the material, you could check out this paper and some others. This is one example here, and I know that this one is iron oxide. So you have iron nanoparticles, and it's at low weight percent, and so you can see that they get dark in a hurry. And so they can build these magnetically susceptible particles into an SLA print. And then what they demonstrated in this right here is that they used magnetic stimulus to actuate a gripper. Oh, hold on. I can erase this here. Bear with me. So in this paper, they use magnetic stimulus in order to order the composite internally, and you can see different ordered layers right here versus right here. And in this demonstration, they basically built a magnetically susceptible device that could be magnetically actuated to pick up whatever they were interested in. So it's two different sorts of ideas for using magnetically responsive materials in different ways. And what's cool is there's a lot of different applications for this. So yeah, using magnets to move stuff around, that's fine. That's a nice demonstration. But even in this simple example, and so what they did in this paper right here was that they did direct ink writing. So again, this is material extrusion AM. And all they did was make an iron-filled silicone, which is what PDMS is. And so now this composite is going to be stretchy. And so they're going to build a composite component using additive manufacturing that's both magnetically susceptible and stretchy. And so this is nice because they characterize the viscosity as a function of shear rate. So we go back to the basics. So what is it going to take to do material extrusion AM in direct ink writing? And so they have a shear, thinning, fluid. And they have high viscosity at low shear rate. So this is going to show thixotropic or zero shear behavior or Bingham plastic type behavior. So you'll be able to create objects that are static, and so you can cure them because you have to cure that. And you see the modulus as a function of shear stress. So this shows high modulus. Which will enable printing. So the same things that we talked about when we talked about material extrusion AM in direct ink writing. And so they characterize the bending angle that they can achieve with this. They characterize the magnetic susceptibility if you're interested in things like that. That's just all the basic material characterization. And so what they did with this process was that they created a butterfly that flaps. Okay, that's very nice. But that's just a demonstration. It's not as useful as saying making a gripper. So by removal of the magnetic field, you can grab the object. That's very interesting. But we've seen that before. The most important part of this paper is this right here. And this is something that not lots of people think about unless you're in the world of antennas or electromagnetics. And I know some of our double E friends are interested in things like this, where you print a conductive grid that's stretchy, and then based on the magnetic actuation, you can get that grid to deform. And what's interesting about this is that this grid has different EM shielding or a different metamaterial bandwidth in electromagnetic radiation, depending on how the grid is deformed. So when you go from a flat grid to a curved grid, this idea of the terahertz frequency filtering changes. And so this is a little bit in the weeds. And of course, I'm not a terahertz electromagnetic antenna engineer, but this is now cool. You're not doing something like a little demonstration of gripping something magnetic, but you're changing or you're morphing the antenna using a magnetic field in order to get a different bandpass in a really interesting frequency regime. And you can see that based on the magnetic field and this idea of what they call the normal test. So they're looking at the frequency absorption, and the decibels here is just a function, or is just a measure of the throughput. And so this gets to be really cool because now using this responsive technique combined with additive manufacturing gets you something that might have useful applications in communications or sensing or something else. So I wanted to bring that paper to your attention because there's only so many flapping butterflies that we can look at and think about, is this interesting or not? But there are an awful lot of people interested in this, especially as things like 5G, as communication on different wavelengths becomes really important with crowded EM spectra and lots of Internet of Things devices. And so this is really cool. And this is something to keep an eye on as you progress in your careers. Any questions on that? Any comments?
So that's supposed to be like a frequency selective surface that shifts in frequency if it bends?
Yes.
Is that what you're saying?
Yeah. So Anna, I know that you know a lot more about this than I do. And so yes, the bandpass filter changes its characteristics depending on the bending. And I'll admit, Anna, you should probably read this paper extensively because you'll be able to understand it more than I will. But this is a cool demonstration of combining materials and additive to do something important.
Yeah, I'll have to check it out. It sounds pretty neat.
And this is not new electrical engineering, because I think every antenna engineer knows that if you change the shape of the antenna, you can access different phenomena. But what electromagnetic engineers sometimes don't know is how to deploy different material systems in different shapes in order to realize some of these concepts. And again, this is where the interdisciplinary approach of material scientist, an additive manufacturing engineer, and an electrical engineer, when you combine all of your superpowers together, you can really get something that one of us can't do alone. And so being able to, say, play a role in how do you formulate the ink, being able to play a role in what type of nanoparticles should I use, or being able to say, well, you really need to do your direct ink writing like this. You know, it would easily take 3 or 4 of us in class in order to make this a reality, rather than, you know, an antenna engineer saying, well, it would really be nice if someone would invent this technology, because I know by theory this bandpass in the terahertz will work. And so this is where we need to get comfortable with each other's skills and be able to access those when we need them. So, Anna, if I'm completely wrong about this terahertz bandpass filter, feel free to email me and I will issue a correction. But this caught my eye because now this is a lot cooler than a flapping butterfly or some magnetic gripper to me. And it turns out there's lots of stuff out there like this. Any other questions or comments on this? Okay, so that wraps up PowerPoint lecture 12. And so if we go back to Box, we are going to switch over to 13. And so I've had a lot of questions in the last few weeks on, you know, is this economical or should we print this? I think even in class we had some discussion of, you know, how do you know you should print it, or what's the idea with printing? So I just wanted to put together a couple slides in terms of process and economics and thinking about what the ramifications are if you decide to print something or not. So there's this famous plot right here, and if you're interested in the source, it's right there. And so if we're a company and we make rubber duckies, so this is a kid's toy that goes in the bath, and this is made out of plastic. There's, let's say, 2 ways that we can make this thing. We can have an injection molding factory and injection mold this, or compression mold it, however they're done. But we can do a conventional process. So this is conventional industrial process. Great. We've got that. Or let's say we want to push the envelope here. We could 3D print this duck. And let's say they're the same. Customer acceptance would be the same. Looks great. So to start an injection molding factory, we need to buy injection mold machines. We need a factory. This is high volume production. But if we make a bunch of parts, our cost per unit goes down. And cost per unit is called economy of scale. And so if you make 1 duck, it's going to be very expensive because you have all that capital cost. But if you make 1 million ducks, you can spread the cost of all your capital out over all those ducks, and you have much lower cost per unit. And this exists for cars. This exists for airplanes. This exists for clothes. So if you want, you know, 1 hand-built car, it's going to be expensive. If you want a Chevrolet, General Motors can really push down the cost per unit because they're going to make lots and lots of cars and they can take advantage of economies of scale. And that's how traditional manufacturing generally works. However, with 3D printing, there's a different cost curve. So the cost curve for AM is different compared to traditional manufacturing. And there's some argument about what is the shape of the curve for 3D. Because of course you need to buy a 3D printer, you need to site it, there's some capital cost in there, all of that stuff. But in general, the community consensus is that the economy of scale slope, or the slope of this line, is a lot different for additive manufacturing than for conventional manufacturing. And you know, when you have lines of two different slopes, in general, they're going to cross somewhere. And they cross at a certain number of units. And the question that a lot of people are asking themselves right now is, where do these lines cross? And if you think about the hearing aid example, the real question is, where do these lines cross for the entire industry? When does it make sense for the industry to do something completely different than what they did in the past? And that's hard to analyze it. There's a lot of different factors that go into that, but this is the very simple picture in terms of, I can make products using conventional manufacturing, or I can make products using additive manufacturing. When does it make sense to do what? Now, additive manufacturing wins when you're making a product that you can't make any other way. So you want to make a Futurecraft 4D shoe with a variable elastomeric lattice in the footbed. You can only do that using 3D printing. Or you want to make a topologically optimized bracket for Airbus A320 or something like that. Additive might be the only way to do that. But there's a lot of products out there that, maybe you can make this with additive, maybe you can make this with conventional manufacturing. How are you going to decide what to do? And so by looking at the cost per unit over the number of units, you can get a better handle on how this works. And so this is a very simple model that you can use as a guide to help guide your thinking, whether you're interested in only low volume, how important is customization, how does labor play into this, how does training play into this, because there are training costs associated with bringing a new process in. So say you have a great factory and you have a bunch of super smart machinists who have been around forever and they know exactly what they're doing with traditional CNCing. And then you bring in a 3D printer and say, machinists, you guys are so smart, please use this 3D printer. They have to learn how to use it. They have to learn how it operates. They have to learn how to maintain it, all of that stuff. And so there is a labor cost and a productivity cost in terms of training. Is inventory important? How much does tooling cost? Internal flow, what does your supply chain look like? And do you incur any costs if you have to do assembly? So say you do injection molding and you have to assemble 20 parts after you injection mold all the components, versus with additive manufacturing, maybe you only have to assemble 2 parts. And so you can save a significant amount of time in terms of labor. And again, this is sort of a basic view of what this looks like, but we're only going to cover this in sort of overview detail to give those of you that have not been exposed to additive manufacturing before some ideas about what people are thinking about in terms of industrializing additive manufacturing. And I think some of this material is presented in other AMD classes. So those of you in the additive manufacturing and design program, you'll have to bear with me if you haven't, if you've already seen this. So any questions about this specific example or about this general theme of the cost curve for conventional manufacturing versus the cost curve for additive manufacturing? Okay, so this starts to get at some of the ideas of why we do what we want to do. And what's interesting, or what people are starting to think about, is how do you make functional parts with additive? And so we're pretty comfortable with using additive manufacturing as prototyping or engineering visioning, or we're just going to mock this up in plastic and see what it looks like. But there's a lot of interest in terms of products, and functional parts equals products, because you're going to sell functional parts. You don't generally sell prototypes or design models. Of course, additive, we're still doing a lot of prototyping. We're still doing a lot of tooling, but there's a real push for making products with additive. And we can see that in hearing aids, in Futurecraft 4D shoes, and other types of additive products, and things that we don't necessarily even know are additive. Like in Ford automobiles now, there's some additively manufactured under the hood components, or in many new airplanes, there's additively manufactured components. And so this is really coming in terms of parts that are sent out the door, and that's important. It's not just models, visual aids, fit and assembly, et cetera, the things that we're comfortable with. Oh, someone asked me a question on NinjaFlex. I'm going to skip this and we'll come back to NinjaFlex next time. Okay. So we'll talk a little bit more about this different process and about the economics around it. If you have questions around economics, and you have questions about how do I know when to additive something, there are classes for that. And so, like I said, we won't get deep into supply chain issues, or we won't develop our own cost models for this. But I wanted to give you some appreciation for, why you should additive and when, and we'll develop that a little bit more. I'll skip the NinjaFlex for now. We'll come back to it. And I wanted to talk a little bit about process modeling to follow along on topology optimization that we talked about last time. And the question is, how do you model process? That's obvious. But you also want to model materials. And you want to model composite components. And we saw a little bit of this in big area additive manufacturing when they were making the Strati. And so Oak Ridge had worked on their thermal model for residual stresses. And so they had a nice process model for that. But people would really like to develop these process and materials models for lots of different additive processes. But it's complicated because right now we have some models for materials. We have some models for composite components. But modeling the additive process, there's a lot of detail that goes into there. And you've seen some of the examples in terms of thermal history. How do you replicate that complex thermal history? Or orientation, depending on the tool path. So if we go back, and let me go back to lecture 12. And I'll bring up this example again. So because the fibers have orientation, so there's orientation in the roads, but then the roads are oriented themselves. So, and depending on both of those things, of course, that's what's leveraged in order to get this complex curvature. But the tool path, or the direction in which the roads are put down and the way that the roads are facing, gives you this second level of ordering that you have to take into account in the modeling. And so, of course, they developed a curvature model for this demonstration, but how do you do this generally? So how do you develop, sorry about that. How do you develop a process model that takes into account all these different levels of orientation? Let me get back to my slides right here. And so when we talk about developing a process model, that's what we're talking about. And people are taking a shot at this. And so there's papers out there, and this is just one in there from the Rapid Prototyping Journal. And you notice that this is 1996. So there are modeling frameworks out there, but they have to be deployed across whatever process we're interested in. And so it's not like everything in additive is brand new and we all have to develop it from scratch, but there's so much complexity that it takes time in order to deploy some of these theoretical and conceptual frameworks for modeling the things that we're interested in. And so this is just a really nice discussion, and I like it because it's a at least older paper in terms of additive manufacturing. The complexity of the problems in even something as simple as fused deposition modeling. And you can read this paper and start to think about, what Joe Bartolai and Tim Simpson have done in terms of road fusion and the physics of molecular interdiffusion and getting good road fusion versus what they've done to compute residual stresses in big area additive manufacturing. And so this is a nice sort of discussion of that. And if we're talking about fused deposition modeling, we really need to think about what are all the thermal stresses in the material and the thermal history of the material. And so we have at least 4 FDM. Thermal history, thermal stresses, road adhesion, and of course we've got orientation. Oh, that's, no one's going to be able to read that. Plus etc. So this gets complex very quickly, and we can make a similar list for stereolithography. We can make a similar list for SLS. We can make a similar list, not with all the same factors, but with the different aspects of the process for polyjet, etc. And so these are things that we can talk about in detail depending on the class's interest or things that you can develop in your own work or issues that you need to think about as if you take this on in your own research. So this is just one example of how complex the heat maps are. So one of the interesting things that people are working on is how do you develop composites models for 3D printing? So this foundry modeling from MIT is really built for PolyJet. And so we saw in the 4D printing examples that they were using a PolyJet printer in order to get their 4D printed responsive structures. And so now this is PolyJet hard plus soft material. So it's Vera white and Tango black. And so if you have two different materials, and if you have a PolyJet printer, how do you design something as simple as a tire using hard and soft composite materials when you can put those two different materials anywhere that you want? And so what sort of modulus do you want? What stiffness do you want? Well, where? You know, of course, in the center of the wheel where the hub is, this needs to be stiff. And so that's going to be Vera white because that's a stiff material in PolyJet. But you notice out here on the sidewall of the tire, this is a composite because it can't be completely rubbery on the sidewall because the sidewall of the tire has some mechanical function as well. And of course, if you look at a tire, we have belts in a tire. So if it's an old term, but now we have what are called steel belted radial tires. That is the reinforcement in a rubber tire. And if you've ever seen on the highway, those wires sticking out of something like a disposable tread on a semi-truck tire, we have steel belts in all our car tires. If you cut them open, there's steel in there. And that's what steel belted radials are. But it's a composite of steel wires which reinforce the rubber structure. And of course, we have rubber on the outside because we want the tires to stick to the road. So the question is, if you're going to design products with this idea, or if you're going to design composites, what sort of software can you deploy that allows you to help design these structures where then you can just print the composite as is? And so this is not only of interest to MIT, people like AutoCAD are interested in this, people like SolidWorks are interested in this. And so it's a new paradigm of composite design based on the characteristics of the printer. So this is design based on reality, or based on the realities of the printer. And that's different than how CAD software has been designed in the past. Because of course, if you dial up SolidWorks, it doesn't know that you're using a CNC machine, or it doesn't know that you're doing injection molding, or it doesn't know what process you're using unless you start to tell it, I'm using this material. These are some of the things that I put in there and an FEA analysis. But now you can think about software where you have a drop-down menu on SolidWorks that says, I'm using an FDM 3D printer with these characteristics. And then the design software helps you make choices in the design based on the characteristic of the printer. And so this is a new frontier that some of you will use in advanced design. And that's very interesting for thinking about the digital design and how the software is coupled to the process. And we have not really had this before, other than an extremely specialized software for some processes. But now this is being developed for all kinds of mechanical design. So I don't know if anyone out there is a mechanical engineer or does a lot of design software stuff. I know some people use AutoCAD or SolidWorks and they're familiar with how those packages work. But this is what's coming next in terms of design software that leverages knowledge of the 3D printing process. Any questions out there? Okay. I think we'll skip this. This is just one example, and I think that this link is dead, but I have to check it. But what's important is that now thinking about how different design inside the shape can influence the performance of the device. And so we talked about this in terms of mechanical properties. And so, of course, the infill will influence mechanical properties. And mechanical anisotropy. But the infill can also influence thermal properties. Thermal. So when we think about all the different things that go on in additively manufacturing a part and all the different properties that we want, we see heat flow, or this Q double prime in this case. The heat flow across the sample really depends on what the infill looks like, how it's connected. We can do a thermal simulation to figure that out. And of course, in a conventionally manufactured part, we might just have something solid or something hollow. But we could never put in this linear crossing or zigzag or hexagon. And so not only are we designing for metamaterials in terms of mechanics, but we can have thermal metamaterials. We can control the propagation of thermal gradients across our component, depending on what the infill is. And this is a real advantage of additive manufacturing. Oh, this is just one last slide that I'll talk about in terms of shape fidelity and process. And so when we think about design software, so we're thinking about design to reality with CAD software that knows about the printer. The CAD software can be a lot more realistic in terms of what the actual printed part is going to be. And so we discussed this before in terms of here is the CAD model. And so that's the desired shape. This is the actual model. That's what you get. And so you can create a calibration curve for that, or the software with knowledge of the process can create a calibration curve and adjust the dimensions of the model in order to get something that's a lot more has a lot more shape fidelity to what you might want, rather than you saying, okay, printer, I need something that's exactly 16 millimeters wide with a 4 millimeter diameter hole in it. This is what I want printed. Of course, the printer is going to give you something different. But if you could take this CAD model with knowledge of the process, you can have software correction of the geometry for successful printing. So again, this is, oh, go ahead.
I was going to say, I think there's some companies that do something kind of similar, like a Mark Forge, their Metal X machine. They do something kind of similar where you give them the model and their software adjusts because it's a extrusion based process with metal powders, but their software oversizes the print so that when it centers and reduces size, it's back to the initial model. So it's similar.
Yeah, Kyle, that's a great comment. And so this Mark Forge printer, like you said, they have to sinter it. Does the software do the anisotropy where different pieces of the component have different shrinkages, or is it an isotropic model, or do you know?
I'm not 100%. I just know that's one of the things that they tout when they're advertising is that their software handles it so to make it back to the original model. So I would assume it's per feature. I don't know. That sounds like a lot of work.
Yeah. Well, no, that's exactly, and I appreciate that. I didn't exactly know about Mark Forge software, but that's exactly the genesis of this idea, that the design software now knows about the printer. And so whether it's a proprietary software like Mark Forge that's built just for their printer, or it's an open source piece of software like Tinkercad that you have a FDM drop down, this is the process I'm going to use, or SLS. This is exactly what companies are doing to make additive manufacturing more useful. So I'll look up that Mark Forge software, and it's likely that they're trying to build in per feature or with the anisotropy. But like you said, that's computationally very intensive, and you know there's a lot of variables in that in there. But I would encourage you all, if you're interested in this, to look around and think about how the software now can adjust to with knowledge of the printer. That's a good comment. Appreciate that. Any other comments? Okay, I think we'll leave it here. We're a couple minutes over time. I apologize for that. But we'll continue this conversation next week. And if you have questions on projects, or if you want to cover topics that we're not covering, or you get interested in something, let me know. I'd be happy to discuss with you over Zoom or take feedback by email. And so I will see you on Zoom on Tuesday. Thank you very much.
Thank you.
Thanks.